Hi, welcome to Lesson 25. We're talking about hypothesis testing. While we will introduce test statistics and p-values, we're not going to be talking about the conclusions and significance levels. Not yet. That's for later. So we're actually going to be talking more about the hypotheses themselves, setting them up, and then briefly introduce the idea of a test statistic. Okay, so like when we were doing an estimation problem and calculating a confidence interval, we will have a certain guide and steps that we will follow. And the first few, they're going to look really similar to last week when we did confidence intervals. So our first step is going to be to state the question of interest. For hypothesis test, this should be like a yes or no style question. So is the average tuition cost for all Oregonians higher than X amount or something like that? Step 2 is going to be identical to last week. Identify the parameter of interest / take inventory. So if we are dealing with 1, 2, or more populations, at least in Stat 201, we're going to pretty much stick to one population. And then what type of variable are we collecting? If it's categorical, we're looking at testing a proportion. If it's quantitative, we're going to be testing the mean. At least for week 7 and 8, we're going to be sticking to a quantitative variable. And then 3, choose a significance level. So this is similar to choosing a confidence interval, except here we're going to usually pick between 0.01, 0.05, and 0.10. And then this is the step we're focusing on in this particular lesson. State the null and alternative hypotheses. And then it's good to ask yourself, is the alternative hypothesis one-sided or two-sided? Check the conditions for the test. So these are going to be really similar to when we were looking at confidence intervals. Do we have a random or representative sample? Is our sample size big enough that the central limit theorem will kick in and that we know the sampling distribution of X bar is roughly normal? And then for this week anyway, do we know the population standard deviation, sigma? If you do, go ahead. We're going to run this test, specifically a z-test this week. Otherwise, there are other options you could use. And then calculate the test statistic and p-value. That's a whole other lesson that we will focus on. And a lot of times it's become more and more common that folks will also calculate a confidence interval. A lot of times it's helpful to follow up, hey, is the average different than this? Yes. Well, people usually will want to know, hey, what is the average? And then return, similar to with the confidence interval, you have to actually return and make sure that you answer that question of interest in full. So the hypotheses. So there are going to be 2 that we look at. There's the null hypothesis. It establishes the claim. So it's not what you're interested in finding. It's just establishing, hey, this is what the website claimed. Or maybe this is a value of interest. We always assume by default that this is true. Usually the null hypothesis is boring, right? It's not what we're trying to prove is true. It's a statement of equality. That means there's always an equal sign in it. We're trying to set it up to reject it. So we're saying, hey, you know what? Let's assume the average really is 94 minutes as claimed, the average trip time on this train. Then we're going to try and find evidence against it. And then it's denoted by an H, and then that's a 0. Or H not. So like not means nothing, or zeros, right? So then we have the alternative hypothesis. So the alternative is the hypothesis that reflects what we're actually interested in finding. So if we think, we think the average tuition cost is higher, this is where this alternative hypothesis is where that's going to be reflected. So it contradicts the null hypothesis. So in a way that only one hypothesis can be true at once. So if you have enough evidence to say the null isn't true, what you're implying is that means the alternative must be true, kind of thing. It can be one-sided or two-sided, and we'll talk about what that means. And it's denoted by H with an A. So you might see a lowercase a or H sub 1. Any of those is acceptable. I'm going to stick to this notation here, A for alternative. And so we like to go, the null is dull, right? So the null is not interesting. It's not what you're trying to find. It's whatever just established norm there is. So some comments about hypotheses. So it's really, really important that you write the hypotheses before collecting sample data and looking at the sample data, right? It's the idea of placing your bets before a race, right? You don't watch the race and then place your bet. You have to place your bet before the race. So your hypotheses, they have to come from the problem before you actually run any of your data. And it's always about what's in a population. So never will you have anything like a p-hat or an x-bar. We will never have information that's about the sample in our hypotheses. Never. And then we will use data from our sample to test the hypotheses. And we're going to be looking at, okay, well, based on what we saw in the sample, how comfy are we saying that we think that the null is false and that the alternative is probably true? So this comfortableness, we have to start by default believing that the null is true. So if the null is true, how weird is what we saw in the sample? That's kind of what we're getting at. And if it's really weird, maybe we don't believe the null is true after all. So back to our example here. So here we have our train, and it's advertised to take 94 minutes. So the train website states the train times vary on average 10 minutes. Here's a big part of what we're interested in here. A frequent rider is consistently late and convinced the average ride time is longer. So here, we do not want to use any of this information because it's from the sample. Nothing from the sample should make its way into the hypotheses. So here, my hypotheses, I'm going to start with, so my null alternative here. So what should go here? So X is train trip time. And I'm interested specifically in the average, right? Because the train trip times, they're in minutes, they're quantitative. I would take an average. That would make sense. And remember, in the null hypothesis, there should always be an equal sign. What goes here is the claim. So this website, it claims it takes 94 minutes. So 94 minutes. So not only do you want 94, you do want its units. For the alternative, it's going to look almost identical. You're still going to have mu, and you're still going to have 94 minutes. But the sign that goes between has to come from here. So here we have the frequent rider is consistently late and is convinced the average ride is longer. That's what we want to look for. So if it's longer, that means the average trip time is going to be higher than 94 minutes. So that is my alternative hypothesis. So by default, we're going to assume they're correct. It really is 94 minutes. The alternative is saying no, it's higher. So now we want to talk about one-sided versus two-sided alternatives. So you can have, there are two ways to get a one-sided alternative. So if you are testing, hey, I think that mu is less than some number. So you want to look at what's called a lower tail. Or if you want to test that mu is higher than some number, like with the train trip example, you would use an upper tail question. So they both use specific kinds of language in the type of problem. So you might want to say, oh, what is the probability that the average is smaller than, or less than, or at most fewer than? There's that kind of language. There's more ways to say it, but those are some very common ways. Versus larger than. You might look at higher than, greater than, at least, more than. There are a lot of ways to say this. So these two, you use these when you suspect that it's either higher or lower than claimed. However, if you just want to see if it's different, this one is your two-sided alternative. So you have to make sure it's not higher, and you have to make sure it's not lower. So does the mean differ from some claimed value? The big difference here is you have a not equals sign here. Here you have a less than sign. Here you have greater than. If it's a not equal sign, it's a two-sided. So look for language like different than, other than, not equal to. Like, is the mean not equal to 94 minutes? That would be two-sided if we did something like that. So now we're going to practice. We have a handful of them. So I'm going to go ahead. I'm going to fill these out. I recommend pausing here, and then I'm going to go through each of them. Okay, so here, one-sided or two-sided alternative. We want to read each line and decide one-sided or two-sided. So the first one, the average time to finish a maze is not equal to. So is not equal to should make me think two-sided. Our second one, the average running pace is less than 7 miles per hour. I can tell you my average running pace is a lot less than 7 miles per hour. So is less than? I'm only interested in looking if it's less than 7. I don't care if it's higher than 7, only less. So this will be a one-sided. The third, the average weight loss is more than 15 pounds. So more than should be where I'm focusing. I only care if it's higher than 15 pounds, so this is another one-sided. The average IQ of OSU students is greater than, so I only want to know if it's higher than. Also one-sided. The average exam score is different than 75%. Different than. So it could be higher, it could be lower. You have to check both sides. This will be a two-sided test. And then the average lunch break is fewer than 30 minutes. I know for sure in California that's not legal, but I know it happens. So this will be one-sided. And so when we start talking about getting the evidence and comparing that and making a conclusion for the hypothesis test, this is where the sidedness matters. Basically, if you have a one-sided p-value and it's a two-sided test, you have to multiply by 2. And we'll get to that when we get to that part of the lessons. So here's a question. We're going to use this one on this slide and the next slide. We have a soda bottling company, and they go ahead and they fill their soda cans, I guess, with 20 fluid ounces. At least that's what's advertised. And the companies really want to make sure that the average fill is 20 fluid ounces. So they go ahead, they hire a firm, and they want to see if there's evidence their bottles are being filled more than what they're advertising on average. So this is really important because a lot of companies don't like to give too much product. So there are reasons. They don't want to give away free product, and they also, if they overfill them too much, they probably can't seal them properly. So definitely very motivated to not give too much. So what is the null hypothesis? So the null hypothesis, remember, should be that the average is equal to something. So I'll give you a second, and then I'll read through and show the answer. Okay, so like I just said, with a null hypothesis, it's saying, hey, it's equal to some claimed amount. So I'm going to go ahead and underline, is more than? No, this right here, this would be good for the alternative hypothesis, right? So alternative is less than? No, we're not getting equal to. Is equal to, yes, is equal to and 20 fluid ounces. That's what was claimed. It should be C, but then we'll double check. Is different than 20, so no. Different than is a not equal sign. More than is greater. Less than, equal. So still on this example here, we might want to ask ourselves, what is the alternative? So I did point out in words, like which of the last ones was the alternative. But the alternative here in symbol notation, so I have mu, and I should still have 20, and I'm going to write FLOZ, so fluid ounces. Now I need to figure out what goes here. It's not going to be an equal sign, so it could be not equal, greater than, or less than, but we need to read the prompt and make sure which it is. So they want to know whether there's evidence their bottles are being filled more than. So I'm going to have a greater than sign. They're only interested if they're overfilling on average. So this is a one-sided test. So when we go ahead and we calculate, we have our hypotheses, we go ahead, we calculate a test statistic and find a p-value. So it's very similar to standardizing. So here, a test statistic, it takes what we observed in the sample, so our point estimate. So most of the time this is going to be x bar, and it's going to subtract a claimed value. So if I were looking at the soda example, minus 20 fluid ounces, and divided by our standard error. So this is going to be that if we're dealing with a sample means and population means, sigma of x bar. So here, we want to know, assuming that the null hypothesis is true, and the mean really is whatever claimed value, at least for this week and next week, we want to know the probability that we would have seen what we observed in the sample or something more extreme. So this is my p-value. So the p-value is saying, hey, let's assume the null is true. How weird is what we saw in the sample? So the p-value, no, it is a probability, so your p-value has to be between 0 and 1. If your p-value is higher than 1, that is a great way to say, hey, something went wrong. Let's go back and check what we did. Okay, so that's it for lesson 25. We're going to start talking about calculating, we're going to actually go through and calculate a test statistic and a p-value and talk about writing up a conclusion.